You saw that low RPM rotor stall was the second primary cause of fatal accidents in the R-22. What is rotor stall? Don't confuse rotor stall with retreating blade stall. Retreating blade stall occurs in high-speed flight when the forward flight speed of the helicopter subtracts from the rotational or tangential velocity of that retreating blade. Stall occurs out toward the tip, which causes some vibration and control system problems. Retreating blade stall occurs and is much more severe in multi-bladed articulated rotors than it is in two-bladed rotors. Actually, in the case of the R-22, we don't experience retreating blade stall at all. We have a very difficult time in our certification programs even demonstrating the beginning or onslaught of it to the FAA. But what is a problem in the R-22 and in all helicopters is low RPM rotor stall. In the case of rotor stall, the rotor can no longer produce enough lift to support the weight of the aircraft. And when that occurs, the aircraft will literally fall out of the sky. What are the mechanisms of it? How does it work? Well, first of all, let's take a look at an airplane, because the rotor stall in a helicopter is almost exactly the same thing as stall in an airplane. In an airplane, the lift that's being produced by the wings is proportional to the angle of attack multiplied times the square of the velocity or forward flight speed of the airplane. The angle of attack is that angle between the chord line or center line of the airfoil and the relative wind. In other words, the air that the wing is contacting as the aircraft moves forward. Now you must understand that in a heavier than air flying machine, the lift being produced by the wings or by the rotor must always equal the weight of the aircraft in any steady state flight condition. So if I reduce the velocity or forward speed of the airplane, then the angle of attack of those wings must increase, because when multiplied together they must always equal the lift or the weight of the aircraft. For instance, to practice a stall in an airplane, I do that by coming aft with my stick, bringing the nose of the airplane up, and reducing the airspeed. As that airspeed comes down, then to produce the same amount of lift, the angle of attack must go up. As the airplane goes slower and slower, the angle of attack goes higher and higher, and finally that angle of attack will reach the critical stalling angle of attack for that airfoil under those conditions. When that occurs, instead of the air continuing to flow smoothly over the upper surface of the airfoil, the air will suddenly separate from that upper surface, will become completely confused and turbulent, and even flowing backward in close to the top of the airfoil. When the airfoil stalls, two things happen. One, there is a loss of lift. And two, and equally important, there will be a very large order of magnitude increase in drag. In an airplane, to recover from that stall, the pilot immediately goes forward with his stick or his wheel to reduce the angle of attack below the stalling angle of attack, so that he can get rid of that very large drag that has been created by the stall. At the same time, he adds power so that he can regain sufficient airspeed so that he can maintain level flight at an angle of attack below stall. That's the way that it works in an airplane. Now, how about a helicopter? Well, in a helicopter, it really works the same way. There's only one difference. Instead of the lift being related to the forward flight speed of the aircraft, in the case of the helicopter, the lift is related to the RPM of the rotor. And the lift being produced by that rotor is proportional to the angle of attack of those rotor blades multiplied times the square of that RPM. In a helicopter, a similar thing happens when you allow the RPM to go down. When the RPM is allowed to decrease in the rotor of the helicopter, then the Angle of attack of the rotor blades must increase. As the angle of attack of the rotor blades increases, eventually it will increase to a point where the rotor blades will stall, just like the airplane wing stalls. And when that occurs, there again, there is a loss of lift and a very large order of magnitude increase in drag. In the case of the helicopter rotor, that large increase in drag acts just like a great big giant rotor brake. And where that RPM may have been coming down fairly gradually, all of a sudden when that rotor stalls, the RPM will suddenly drop immediately. And the helicopter will literally fall out of the sky. In the case of the airplane, when the wing stalled, the pilot could always recover from that stall. He could recover from the stall by pushing the nose of the airplane down and dive the airplane to reach an angle of attack below the stalling angle of attack. Even if he had to push the nose all the way down to 90 degrees, he could do it in an airplane and recover from that stall, provided he had sufficient altitude. Not so in the case of the helicopter. Once that rotor stalls in a helicopter, and the helicopter starts to fall out of the sky, there will be an upward flow of air going through that rotor that will increase the angle of attack. The relative wind, instead of being horizontal, as I've indicated here, now will be coming up at a very steep angle. That, combined with the much lower speed of the rotor blades, will increase the angle of attack to such a high value that even with full-down collective, I will not be able to reduce that angle of attack below stall. Because even with full-down collective, I still have typically 2 or 3 degrees of positive pitch. So that's rotor stall, and it's something which must be avoided at all costs. No matter what you have to do to maintain that RPM, you must do it. It's better to go ahead and allow the helicopter to settle into some trees or bushes or something else than to allow that rotor to stall and the helicopter to fall out of the sky.